A very good day to Dr. Firdaus and all my fellow friends. I'm Siew Ying from SSCF, and this is my presentation for Microscopy and Material Analysis course. Today, me and my friend Joo Yi would like to present a topic about atomic force microscopy, which can also be called as AFM. So let's get started. Before entering to our main content, let's go through some history of AFM. In 1981, there are two scientists from Switzerland who are Gerd Binning and Heinrich Rohde design and build the first scanning tunneling microscope STM. Binning and Rohde show that by regulating the vibrations of an instrument, the electron tunneling current between a sample and a sharp probe can be tracked. However, it can only image conducting or semiconducting surfaces. So people try to extend the STM technique to investigate the electrically non-conductive materials like proteins, polymers, ceramics, composites, glass, or biological samples. In 1986, Binning and Rohde received the Nobel Prize for the invention and design of STM. Actually, this year, they only received half of the Nobel Prize, while the another half goes to Ernst Ruska for his fundamental work in electron optics and for the design of the first electron microscope. But anyway, as I said just now, the STM only applicable on conductive surfaces like metals. So after 5 years of the STM's invention, Binning, Christoph Gerber, and Kelvin Kuet invented the atomic force microscopy. Their original AFM consisted of a diamond shard attached to a strip of gold foil. The diamond tip contacted the surface directly with the interatomic van der Waals forces, providing the interaction mechanism. Finally, the detection of the cantilever's vertical movement was done with a second tip, which is an STM placed above the cantilever. This AFM can be used with non-conductive surfaces and can also be used like the STM to position objects as small as an atom. By using an ultra-small probe tip at the end of a cantilever, the AFM could attain very high resolutions. To dive into a deeper knowledge of AFM, we need to know what exactly is an AFM. So AFM is a type of scanning probe microscopy, SPM. Since AFM is the most popular type of SPM, causing the terminology of AFM and SPM to be often used alike. SPM forms images of surfaces using a physical probe that scans the specimen. This goes to the AFM. The high resolution mapping of surface topography by far is the biggest application of the AFM. It can offer image resolution down to the atomic scale. In case of AFM, the prop is a cantilever, generally having a tip at its free end. It uses a sharp tip on the end of a flexible cantilever to feel or touch the sample surface. When it scans very closely across a surface, it will detect forces present between the surface and the tip. The basic operation principle of a standard AFM system involves scanning an AFM probe with a sharp tip over a sample surface. So, the tip plays an important role in AFM. Basically, AFM consists of a sharp tip that is approximately from 10 to 20 nanometer in diameter, which is attached to a cantilever. The radius of tip limits the accuracy of analysis or resolution. So, when you see the two figures at the right hand side, when the smaller radius tip slowly moves over the surface of a sample object or material, it can simply touch the sample if compared to the larger radius tip. Besides, AFM tips and cantilevers are microfabricated from silicon or silicon nitride. There are three common types of AFM tip, which are normal tip, super tip, and ultra level. It may also be coated with other materials for the additional scanning probe microscopy application, such as chemical force microscopy and magnetic force microscopy. AFM is a powerful technique that enables the imaging of almost any type of surface. The analysis provides image with near atomic resolution for measuring surface topography. First, it is capable of quantifying surface roughness of samples down to the angstrom scale. In addition to presenting a surface image, AFM analysis can also provide quantitative measurements of feature sizes, such as step heights and other dimensions. Additionally, advanced modes of AFM measurements allow for the qualitative mapping of various other physical properties such as adhesion, modulus, Doppler distribution, conductivity, surface potential, electric field, and magnetic domains. As you can see, the cellulose, nanofibers, and aluminum alloy, AFM is a useful tool to capture the 2 and 3-dimensional image of height and size of nanostructure object. Next, let us move to an example of AFM imaging. So here is a research about the aluminum doped zinc oxide film by solder process for integrated optics. So the undoped and aluminum doped zinc oxide thin films are prepared by the solder process and went through the deposition of 7 successive layers to have a thickness sufficient to observe. The researchers are trying to find the best compromise to obtain a material with a low roughness. So, differences in surface roughness obviously lead to visual differences. However, they also have an effect on a variety of other characteristics. Example like the amount of wear, the ability to form a seal when a part makes contact with another surface, and the thickness of the pen needed to cut a part. So, this is why it is necessary to quantify surface roughness. Back to the topic, this table lists the result of the experiment on the undoped 1 atomic percentage of aluminum dope and 2 atomic percentage of aluminum dope. So there are 3 figures which represent the AFM image for the zinc oxide surfaces. From this image, the root mean square roughness value can be extracted and seems to be significantly dependent from the aluminum content. The undoped 7-layer sample would present an RMS of 11 nanometer. This value would decrease to 7 nanometer for the 1 atomic percentage of aluminum sample, whereas a 2 atomic percentage of aluminum sample would present an RMS value of 4 nanometer. From the AFM observations, the flatness of the film is greatly increased with the aluminum content, and thus using aluminum doped zinc oxide may improve the waveguiding properties of the films, which are directly dependent on the roughness. That's all from me. I will now move my turn to my friend Joo Yi to bring you explore more on atomic force microscopy.
Hi, I'm Joo Yi. So I will explain the working principle of atomic force microscopy. The basic AFM will consist of laser, a detector, and cantilever, and a sharp probe. So this is the force showing when the probe approach the sample. So we can notice from this if as the tip approaches the surface, the attractive force is created between the tip and surface, causing cantilever to bend. So this shows that the uh, distance between the probe and the sample is decreased. So when cantilever gets even closer to the surface, the repulsive force will increase. This is the repulsive force showing the repulsive force increase and cause the cantilever to bend away from the surface. This figure shows the AFM scans the sample in constant force mode. The Z scanner will move the cantilever up and down. Hence, the Z scanner will compensate for the cantilever amplitude, and hence this cantilever amplitude will keep constant. However, the SY scanner will move the sample back and forth, so the vertical tip, which is also called as the probe position, will become high and low. The principle of AFM is there is a laser will strike the laser beam onto the tip surface of the cantilever. Hence, the signal will reflect to the photodiode detector. Hence, there is a feedback loop which we're using the laser deflection to control the force of the cantilever, to control the distance between the probe and the sample. To operate AFM, firstly we can prepare a sample with typical size which is 8 times 8 mm with height of 1 mm. If the sample used is in solid or dispersion state, we are recommend to apply a uniform of layer material by spin coating the solution to allow the particles stick to surface. The figure shows the setup of instrument. After the instrument is set up, we can choose we want contact mode or tapping mode. There are several precautions when using AFM. If the sample is contaminated, surface charge may produce the false feedback and cause the image blur. To solve this problem, we can increase the set point value by increasing the amplitude of vibration and thus can create a conductive path between the cantilever and sample. Besides, there are another precautions we need to take note also because the image quality will also depend on the tip size and shape. If the tip is not perfectly sharp, this may not provide a best aspect ratio of image. Besides, if the tip is blunt or broken, this will cause a false and poorly constructed image. AFM is divided into two modes which are contact mode and tapping mode. For contact mode AFM, the cantilever will scan across the sample with tips touching the sample surface. When the tip is approach the sample, there is a strong repulsive force which will causing the cantilever to bend. We can see from this if the tip is scans across the sample. Okay, so this contact mode is preferably used for hard sample. The advantage of contact mode AFM is simple and not too affected by humidity, and it is suitable for the sample in liquid state. However, there is disadvantage of AFM, which is easy damage to soft samples because the sharp tip will scratch the surface of sample. Another mode for AFM is tapping mode. In tapping mode, the cantilever will oscillate above the surface. As the tip approaches the surface, the interaction between the tip and surface will cause the oscillation amplitude of cantilever to decrease. We can see from this GIF, as there is a rise on the surface, the tip will also move according to the surface. Hence, the feedback loop will be recorded by correct these amplitude deviations and construct a surface topography. This tapping mode is preferably used for biological samples because these biological samples are normally fragile and prone to damage. The advantage of tapping mode is this can retain the tip sharpness and preserve the sample surface. By retaining the tip sharpness, we can ensure that the image produced is in high resolution. However, this disadvantage of this tapping mode is the scan speed is very slow if compared to the contact mode. There are many advantages of AFM. AFM has easy sample preparation, where the sample doesn't have to be in conductive. Besides, it can give accurate height information of surface morphology of the sample. Furthermore, the AFM can be done in ambient conditions without complicated requirements. AFM can be used to study living systems such as biological samples. Furthermore, AFM is capable for show 3D imaging instead of 2D imaging, which is good for research purposes. AFM can also work in air, liquid, and even in vacuum conditions. The disadvantage of AFM is it has limited particle and magnification range. For example, if the sample is too rough with huge undulation, hence the AFM may not function properly. AFM has also low scanning time, which might cause thermal drift on sample. Tip and sample may also damage during detection. Some of the applications of AFM are study of characterization of nanoparticles. AFM can also use as process control tool in semiconductor manufacturing for defect identification. Furthermore, AFM can measure the surface roughness. Besides, it can also investigate the surface properties of implants. Last but not least, FM can be used to study the phenomena of abrasion, adhesion, cleaning, lubricating, and polishing. That's all for our presentation topic of atomic force microscopy. Hope you guys can learn something from it. If you have any question, feel free to comment below. Thank you.